So good afternoon. I'd like to begin with a short video to wake you up after lunch. We'll start that and then I'll go into my presentation. Is the sound coming? So I hope that woke you up after lunch. I'll try to explain some of the activities that Knorr-Bremse is involved in around the world in high-speed braking systems. I won't only cover brakes. Most of you know Knorr-Bremse as a brake manufacturer, but in the meantime, Knorr-Bremse provides subsystems for all types of vehicles, including high-speed trains, and I will try to explain some of the requirements, not only in brakes, but also in doors, air conditioning, and give you an outlook to the future where things are headed. So starting off, we have 111 years of innovation. Here are some of the references of Knorr-Bremse in high-speed trains around the world. I think there is hardly a high-speed train in the world which does not use Knorr brakes and other subsystems. So we have experience in the coldest parts of Russia with high-speed trains to the hottest parts of Saudi Arabia with high-speed trains where we provide the brake equipment. And all of this experience we can pull together and provide to the train manufacturers. Knorr-Bremse, as I say, provides now a portfolio of subsystems, not only brakes, but also power systems, air conditioning systems, parts of the power electrical systems, condition monitoring systems, the electrical doors, as well as the brake system. And I will go in to talk about some of these subsystems and how they can be affected by the requirements of ultra-high-speed trains. Of course, Knorr-Bremse is a mixed bag, it seems, of these different subsystems. How can we integrate them? How can we get more synergy from the different subsystems that we can provide on a train? And we set out our innovation roadmap to say, what are our goals? We have identified the strategic fields that need development, And we've identified some of the topics which are discussed earlier today. Low life cycle costs, the need for an easy homologation of a subsystem on a train, and then, of course, eco-efficiency. And these are trends that we've identified, and they're common threads that go through all of the subsystems of Knorr-Bremse. So without further ado, I'll go to the brake systems. If we talk about high-speed trains going up to 350 kilometers an hour, or indeed up to 400 kilometers an hour, we see we need to master the high kinetic energies. We need to master the life cycle costs which are involved there. As we've seen, and the experience shows, that if you go much beyond 350 kilometers an hour, you have a significant increase in the life cycle costs of a train. More wear of the brake pad and more wear on the brake discs. Also, the signaling becomes important at higher speeds. We need to show that we can really manage the adhesion and how we best use the adhesion which is available in order to brake or indeed accelerate the train. So overall, we see an optimization of the utilization of modern technologies. To design the brake system for a modern ultra-high-speed train, we have to consider what are the requirements. We have to consider the basic input data, as well as the system design. How are the vibrations in the bogie, for instance? And I think the next discussion will say about the running capability of a bogie and how that would affect the brake system. We have to talk about the brake calculation. The thermal design becomes more and more important at the higher speeds. And then finally, the validation of the brake system, that it can perform under all critical states. If we look at the development over the years, and here you can see the chart going up to speeds of 400 kilometers an hour, where you can see that the brake energy per disc will go up, and as we saw in the film, to beyond 40 megajoules of energy per disc. And if we think about that, 40 megajoules is about the energy that a household in Europe will require for 3 to 4 months. So it's a huge amount of energy in one brake disc. How do we manage that energy in a more effective way? We can manage it by clever optimization of the braking across the whole length of the train, managing the brake control. Which brake discs are we applying the brake to? Can we optimize that application of the brake disc by clever use of both the electrodynamic braking as well as the brake disc requirement, as well as maybe other innovative technologies such as eddy current brakes? All this requires a lot of investment and a lot of optimization, and Knorr-Bremse is continuously optimizing its brake test facilities. And here is an example of a new facility that we've just inaugurated, which shows how we can mount a bogie on a roller rig, enabled to optimize the braking, and in particular the wheel-rail contact. This is part of our R&D center developed in our facility in Munich. If I go on further, and we look at as we saw in the film, it's very important to manage the energy on the surface of the disc to avoid hot spots, because otherwise we will get cracking of the discs. And so one of the pioneering technologies of Knorr-Bremse is to ensure an even distribution of the heat across the surface of the disc. And we've been able to do that, and it has enabled us to get 40% more energy into the brake disc as was possible before. How do we do that? We do that by optimizing the brake pad. You might think this is quite a simple issue, but the amount of intellectual capacity that's gone into developing the brake discs for the high capacity isobar pads is extreme, and now that is used on the majority of high-speed trains, whether in Japan, China, Europe, and elsewhere. We are using this so-called isobar pad for almost all of those applications. because it has proved we can get a very even temperature distribution across the surfaces of the discs. We have tested this on trains up to 400 kilometers an hour, and it has always passed the test. Now I'll move on to the other areas of doors. Doors also have heavy requirements within high-speed and ultra-high-speed applications. The passengers are sealed in. We need to ensure that the pressure waves outside the train do not enter the train, so we need pressure-sealed doors. And we can see the kinematic concepts have developed over the years, from sliding doors to plug sliding doors, with the development of the high-speed trains from the early Shinkansens into the ICE and TGV trains. And the sealing system has also developed. We experimented with active inflatable sealings, but now have gone back to a more stable passive system. So how has this developed? Over the years, we can see this change, and now the plug sliding door becomes more or less the standard in high-speed trains. And I'll go on to show some examples rather than go into detail there. In the early days, pneumatic doors were the standard. But I don't think there are any purely pneumatic doors now used in high-speed application. Everything has moved on with the need for monitoring and the control that electrical doors offer. So what we see is the standard is used across the range, and from about 1995 up until the present time, and used in the trains here, we see the use of electrical drive units and pneumatic compression systems to close the door, ensure they save strut despite the pressures on the outside of the train. This enables to improve the reliability and availability of the trains. We developed that further to all electrical systems used on the high-speed trains from both Siemens and from Talgo, which we saw earlier. And we can see the development of this technology to a full electrical system, allowing the monitoring and reliability of targets to be achieved. So this is the standard, and it's used almost all over the world. But it goes further. What are the next steps? The next steps involved in opening up the train to get a quicker change of the passengers in and out. And you can see the importance of sealing increases as the speed of the train increases. But also, we see an increasing requirement to open up the door space. And I think in India, this may be one of the technologies which we'd need to apply to allow a lot of people to get in and out of a high-speed train quickly. We've already implemented that on a number of trains running in Switzerland as well as in Italy. And here you can see one of the first applications which started a few years ago with a train with a door of 1,600 millimeters in width, allowing more people to go in and out. And we've solved a lot of the problems concerned with installation in the door frame of the train. And this is now a fully passive sealing system, so very robust for different environments. So that's just one idea for you maybe when you're thinking about the future of ultra-high-speed trains for India. Then finally, looking at the application of air conditioning to high-speed trains. Of course, here, we know that the vehicle is pressurized inside. The air conditioning is required to maintain the comfort level inside the train. But as I think in a talk earlier this morning, it was mentioned, there is the problem, what about the high-pressure waves which try to enter the train, particularly when entering tunnels or when a train passes by? And so we need to take that into account in the design of the air conditioning system for high-speed trains. And the pressure variations can be extreme, and that is why we have gone to looking at applications with an active pressure wave detection system, which closes off the entrances to the HVAC system, the air conditioning system, and allows us to damp down the effects of this pressure wave when entering a tunnel. And you can see here, by use of turning on and off the ducting within the air conditioning system, it allows us to maintain the stability of the system and not to cause any discomfort to the passengers when entering a tunnel, which is something we will also, I'm sure, have to consider here in India. It's done with a question of dampers, pneumatic dampers, which are turned on and off as the demand comes when a pressure wave is detected. So that's one area which should ensure that the comfort levels are maintained within the train. Also, for the air conditioning system, one has to consider, naturally, the huge temperature ranges that the train is exposed to. The air conditioning system must function under extreme ranges, very cold and very high environmental requirements. And here, with a nod to my colleagues from both Siemens and Talgo, we can see some of the examples where we've experienced in very cold environments in Russia with the Siemens high-speed train, the Velaro, and in particular with our colleagues from Talgo with the Mecca-Medina train, where new requirements are required. In Mecca-Medina, we had to develop a new type of HVAC which avoids the dust and dirt do not enter the HVAC system, so it has a unique cleaning system which blows out all of the dust at appropriate times to stop the whole system being clogged up. It also naturally has to function under extreme temperature ranges. In Saudi Arabia, you can see from -5 to +47 degrees. So we're used to gaining this experience around the world, and we look forward to having the opportunity of maybe applying this technology and our experience also in India. Now, looking to the outlook, where's Knorr-Bremse heading? Our vision is to try to integrate the different subsystems in a more effective way to find the synergies between the different subsystems. This might help us with monitoring, might help us with enabling one service point on the train so that all of the subsystems from Knorr-Bremse can be accessed very easily. And this is the way we're heading on how to integrate the systems into a common functionality, a bit like when you think of the Internet of Things, the internet on the train. We talked earlier this morning about digitalization of the railway, and I think this is one step in the way. How can the systems interact in a more effective manner? The next area that we're working on is the pre-integrated systems, that we make sure that these systems work harmoniously together from the very beginning. And lastly, as I mentioned earlier in the talk, the homologation, the acceptance testing must be there so that if a train is applied in India, we know that it can be easily accepted if certain characteristics from the subsystems are achieved. Going further, Knorr is developing its technology so that it can follow and link the various systems together, and also to provide the end user with a back office, a cloud, to enable them to monitor the status of the train and the subsystems on the train. So this is something which is the way we're heading for the future, not only for high speed, but it also will also apply to high speed and ultra speed applications. Our vision is to follow a common approach in all the subsystems, from the vehicle specification through the certification process, in the software architecture, to verification and validation, and finally through commissioning to get the maximum synergies in brakes, doors, HVAC, and other subsystems from Knorr. So one example how we might be able to help is by today the need for the train operator, in this case would be Indian Railways or, for instance, Delhi Metro, would have a multitude of service terminals which they have to use to access the different subsystems. With our effort to harmonize our systems across the subsystems, we will be able to provide one service terminal which will allow access and diagnosis information for all of our subsystems within the train. Not only is Knorr-Bremse able to provide the technology, we've also been a long time in India and have spent a great time in localizing our technology, our high technology in India. This is a picture of our plant on the left-hand side. It's on the road to the Taj Mahal. I think many of you have maybe visited it, but really we've invested a great deal in this state-of-the-art plant. It produced to the Knorr quality level and follows our Knorr production system, which is generic across the whole world. And in this facility, which you can see a few shots here, we have the capability to manufacture. Here's a picture of the facility. It looks very much like our facilities, whether they're in Budapest, in Munich, or in China. We have a very similar approach, and we have there the capability to manufacture all of the subsystems I've described in the presentation. And here's an example what we already supply for the passenger coaches, which we're working with the colleagues from Indian Railways to speed up with new technology. Here we're talking about the medium speed 200 kilometers an hour, but we will introduce and localize the technology to ensure Make in India is part of our brand in the future. We also back that up with a service network across the whole country, allowing us to support the products when they're installed. So finally, this has been a very brief introduction and a brief idea of what are the subsystem challenges in ultra-high-speed trains. Some of the common trends we see are energy management, whether it's in the energy management in the brake disc or the energy management in the HVAC. This is the way things are going. How do we optimize the overall system? The other trend that we saw in the presentation is the requirement to be able to survive in different harsh environments. India is a big country. You have a huge range of temperatures across the country. It's very unique in some ways. We can draw on our experience in different environments to provide the right products and the right subsystems. And last but not least is the increasing interconnectivity of the subsystems to improve monitoring, diagnosis, and to indeed optimize them. And that's something that we want to do with you. Maybe a thought might be, if we have the brake system and the HVAC system and the door system connected and working well together, who's to say that when a train comes into the station, we don't maximize the regenerative energy, use it to drive the HVAC, the air conditioning, with the regenerated energy, and then open the doors just at the right moment and turn the HVAC then off before we waste energy. So we see all sorts of possibilities in optimizing the play of the different subsystems. So in the future, we see exciting possibilities in the interplay between the different subsystems, and we look forward to doing that with you, with our partners here in India. Thank you very much.